In this video, we're looking at the first of the practice problems, and this problem gives us the function f of x equals negative x squared over 2 minus the natural log of x squared plus 1 plus 2x times the arctangent, also called an inverse tangent, of x. Let's begin by finding the derivative of this function. Okay, so first of all, we're trying to find the derivative, so f prime x equals, let's take the derivative of negative x squared over 2. Now, negative x squared over 2 means negative 1/2 x squared. We'll use the power rule to bring the 2 down. We actually end up with negative 2x over 2, and already you probably see that those 2's cancel out. Minus, now we'll take the derivative of the natural log of x squared plus 1. The way that the derivative of a natural log works is it's 1 over the argument, so it becomes 1 over x squared plus 1. Of course, now we have to use the chain rule on take the derivative of x squared plus 1, and we get 2x. Not bad. Plus, now we'll do the derivative of this portion of the function. Now, that part of the function is actually two functions multiplied together. 2x times the arctangent of x. So the derivative of 2x is 2. Then we multiply that times the arctangent left alone. Plus, this is the product rule I'm using now. We leave the 2x alone and multiply that times the derivative of the arctangent. The derivative of the arctangent is 1 over x squared plus 1. Now, take a look at what we have here. If you look over here at this term, you see we have a negative 1 over x squared plus 1 times 2x. And over here we have a positive 2x times 1 over x squared plus 1. Those are actually additive inverses. They cancel each other out. So this goes, and that goes, and we're left with our derivative. The derivative of f of x is equal to, remember this negative 2 over 2 went, so this is a negative x plus 2 times the arctangent of x. This could also, of course, be written as 2 times the arctangent of x minus x. Alright, so these are both nice ways of writing out the derivative. Here it is. We'll leave that there for now. We'll come back and use that in a moment. But before we move on to doing something else, let's right now find the second derivative of x. So we're taking the derivative of this derivative, taking the derivative of 2 times the arctangent of x. Well, that is just going to be 2 over, it's 2 over 1, x squared plus 1. Now, what is the reason for that? Well, you see I'll do it over here on the side. I may have gone a little too fast. It's 2 times the derivative of the arctangent of x, which is this, right? And then 2 times 1 is 2. And so we have 2 over x squared plus 1. No problem with that. But this, of course, here is just minus 1. So here we have also found the second derivative. Pretty painless. Alright, so we have these two derivatives. What is it that we're going to do with them? Well, what we really want to do, what we need to do to answer questions about where is it increasing, where is it decreasing, where are the relative max, the relative min, where is it concave up and concave down, is we need to make some sign charts. Alright, so I'm going to make a sign chart. Let's make a sign chart, first of all, for this first derivative. Okay, let's make a sign chart for this first derivative here. We'll put it right here. So here I'm making a sign chart for the first derivative. In order to, I'll indicate that this is, of course, for the first derivative. What do I need to put on my sign chart? Well, I hope that what you have in mind is we need to find the critical numbers. You can't make a nice sign chart without critical numbers. Of course, there could be no critical numbers, which is okay, which means the entire thing is positive or the entire thing is negative, but I think this one may have some critical numbers, so we need to find them. Now, how will you find the critical numbers? Well, the critical numbers are basically the x-intercepts, are the places where the function either becomes 0, the values of x that make it become 0, or the places where it's undefined. So that is the x values where it's undefined. So on your calculator, on the graphing calculator that you either have or were given, you're going to put in for y1, you're going to put in 2 times the inverse tangent of x minus x. And you're going to make that graph using your graphing calculator. You're going to make that graph, and then you're going to type second. You're going to press the trace button after you've made a nice graph. That gives you the calculate menu, and then you go to, and then the second choice, which is to find the zeros. This is where it's going to ask you for a left bound, it's going to ask you for a right bound, and it's going to ask you for a guess. You're going to do those things. Once you have done that, you'll come up with something that looks like this. I've done it over here on I used Wolfram Alpha since I'm using the internet at home. You can make this same graph on your calculator. You can use the second trace to find these zeros. When you do find these zeros, here's what you'll get. You'll see that it's plus or minus 2.33112, so 2.3311, and also 0. So those are our critical numbers. If you've done it correctly, those are your critical numbers. I will put those on our sign chart right now. So one of them was here at 0. One of them is right here. It's x equals 0. Another one was over here at negative 2.3311, and there's another one at positive 2.3311. Now, where is it positive and where is it negative? Well, to do that, you also use this graph that you made. So all of this is coming from the graph that you made, making a nice window, trying to find the zeros, but those are the x-intercepts. You can go back to the graph. I'll go back to the graph. Let's see, what is the function doing when it is to the left of negative 2.3311? Just to remind myself and to remind you, here we are here at, when we're to the left of negative 2.3311, this derivative function is above the x-axis. It actually goes above the x-axis, then it goes below the x-axis, then it goes above again, and then it goes below. So is it good enough to say that here it has to be positive? It must go positive, negative, positive, and negative. One more time. Positive, negative, positive, negative. Go back and indicate that on my sign chart here. So on my sign chart, it starts off positive, then it becomes negative, then it goes positive, and then it finishes it up negative. So now I have a sign chart for the first derivative. I can use this to answer a lot of good questions. There's a lot of good questions that can be answered just by using this sign chart. In fact, that's exactly what I'm going to do right now. First of all, let's find the places where it's increasing and decreasing. So based on this sign chart, I can say the following things. I can say f is increasing. F is increasing. Now, this is the original function. See, this is not the derivative. This is the original function. F is increasing wherever the derivative is positive. So let's find those places. Well, it does that when x belongs to this interval that comes from negative infinity up to negative 2.3311. There's another place it does that also. It does that between 0 and 2.3311. So that's where f is increasing. Let's also indicate where f is decreasing. So f is decreasing on the intervals, well, that's wherever the derivative is negative. So we'll say this is on the interval here, x belongs to negative 2.3311 to 0, right? Because you see how that is the interval? That is the interval where the first derivative is negative. Union with, where else is the first derivative negative? Well, it's negative also from 2.3311 to infinity. Alright, so that's where we have its increasing and decreasing. That's right. If you want a further justification, which is always a smart idea, the AP test will definitely be looking for justifications. A nice way to give a justification for this is we can say that these are the places where, because we made this nice sign chart that shows that we did this. These are the places where the derivative, you see, this is where the places where the derivative is greater than 0. Maybe to show that it's a justification, maybe I can even use a nice word like because. Because the first derivative is greater than 0. And here this is because the first derivative is, I think you know, it's where it's less than 0. That's where it's going to be decreasing. Alright, what else can we tell straight from this sign chart? This thing that I've made right here is what I am calling the sign chart, and I hope you can make one also. Okay, well, another thing I can tell is I can find all the relative min and relative max. Now, first of all, let's find the relative maximums. Okay, f has relative maximums. F has a relative maximum. Well, it has to have a relative maximum wherever it goes from increasing to decreasing. So that's where it's going to go from positive, where the first derivative goes from positive to negative. It has a relative maximum. So right here, there must be a relative maximum because it went from positive to negative. It went from, the it I'm speaking of is the first derivative, went from positive to negative. Therefore, the function went from increasing to decreasing. Right? If it goes from increasing to decreasing, then this must be a relative maximum. It does that again here as well. Alright, so we can actually indicate that there are relative maximums at the values at x equals negative 2.3311 and x equals 2.3311. Should we give a good justification? Yes, let's give a good justification. This is because the first derivative switches from positive to negative at these values for x. Right? That is the reason why. What about where are the relative minimum values? Let's see if we can find those. Okay, here are some relative. Let's find the relative minimum values. Hopefully I can still see my sign chart. Yes, I think I can still see my sign chart if I slide this over here like this. Okay, f has relative minimum at the following points. Well, it's going to have relative minimum wherever it goes from decreasing to increasing. So those are the places where the first derivative goes from negative to positive. So that's going to be like right in here. See here it goes from a negative first derivative to a positive first derivative. So there it has a relative minimum at x equals 0 because the first derivative switches from negative to positive at this value of x. Absolutely right. That's very good. We've really learned a lot about the function. Let's move on to what can the second derivative tell us. Now we're moving on to things the second derivative can tell us. So I'm scrolling back over here. I'm actually looking, reminding you here where we found the second derivative. Right here is where we found this was the second derivative. A nice symbol for the second derivative looks like this. This is d squared f gx squared. This is the symbol for the second derivative, which we found right here. Let's make a sign chart for it. Now, how do you make a sign chart? Well, you make a sign chart the same as we did before. In order to make a sign chart for the second derivative, I'm indicating this is for the second derivative, we need to know the critical numbers. Now, you absolutely could, and I actually recommend that you do, go ahead and go to your graphing calculator. You can clear out what's there if you like, or do another one and put it. Now on your calculator you'll have to be careful how you type it in. I would use parentheses. 2 divided by, here put parentheses, x squared plus 1, close the parentheses, minus 1. You can graph this, and using the graph you can hit second. I'm assuming you have your graphing calculator that you either own or were given to use. Second, trace, choose the second choice, which is zeros. Alright, you can do that. You can use the left bound, right bound, find all of the x-intercepts. When you do that, which is fairly obvious to me, those values will become -1 and 1. Alright, those are the two values where it has x-intercepts. Can you see the reason why? When you put in a -1 squared will become 1, so on the bottom will be 1 plus 1, which is 2 over 1, which is 1, and then 1 minus 1 is 0. So those are the critical numbers. The only question is, what are the signs? Alright, so to do that, it certainly does help to, it probably does help to have a calculator, although this one can be done mentally as well. How about if we choose a value? Let's choose a value that is less than -1. So if you take a number, say like -2, test value. Can we do this part in our mind? -2, when we plug it into the second derivative, -2 squared becomes 4, so it's 2/5. 2/5 now is a number that is actually less than 1. So we have a number that's less than 1, and we're subtracting 1. When you subtract a number that is larger than the number you begin with, it has to be negative, so this part must be negative. On the other hand, let's choose a value that is between -1 and 1, say 0. Always a nice choice when you can choose 0. 0 squared is 0, 0 plus 1 is 1, so this would become 2 over 1, which is 2 minus 1, certainly 1, that's positive, so this part must be positive. If we choose a value that's larger than 1, say 2 again, that becomes 2/5 minus 1 again, which has to be negative. So here's my sign chart. You can either do it by thinking about it, as I just did, or you can do it by graphing it. I think you should probably graph it since you have these nice graphing calculators. But now we have some more useful information about the original function by looking at the second derivative. This is the second derivative sign chart. The first thing I can tell you is that there are inflection points. F has inflection points. F has inflection points at x equals -1 and x equals 1 because the concavity changes at these points. Now, the concavity is really just another way of saying the sign of the second derivative, as you can see by looking at the sign chart at these values. Now let's just go ahead and make that a little more explicit by actually stating what the concavity is and where. So we'll say F is concave. F is concave down on the intervals x belongs to, looks like it's going to be -infinity up to -1, and from 1 to infinity. And the reason why is because because on these intervals the second derivative is less than 0. I'll say on these intervals, or on this interval. And we can say that f is concave up. F is concave up where? Well, it's concave up wherever the second derivative is positive, which we found is when x belongs to the interval -1 to 1. And this is because on this interval, the second derivative, what? The second derivative is greater than 0. That's very good. Alright, this is really pretty much everything that you were asked to do. There was one other thing you were asked to do, which I'm going to leave that for you to work out on your own, since you have a nice graphing calculator that can do all the work. Another part of the question was, there was this last part of the question which asks, what is the absolute max and min on the closed interval 1/2 to 3. Okay, so the way that these work is you have to use your endpoints. These are the endpoints. And you use any of the critical numbers for the first derivative that fall between those endpoints. Now, if you go over here, you'll see that there is one critical number that falls between those endpoints. See, that's 2.331 for the first derivative. Alright, so let's see here. So first of all, there are the endpoints. The critical number that falls between those endpoints is 2.331. So what you need to do now is you have to go back and use the original function. Now, this is the original function. Find what is f of 1/2. Find what is f of 2.3311. And find what is f of 3. Okay, I'm going to leave that for you to do. Remember, you're using the original function now. The 1/2 is an endpoint. 2.331 was a critical number for the first derivative that falls between 1/2 and 3. And 3 is an endpoint. You're going to find these three values. The smallest of those values is the absolute min, and the largest of those values is the absolute max. Okay, so this was a nice example of exploring a function by finding its first and second derivatives, making a nice sign chart, and then using the sign chart to find the important features of the function that we began with.